review session. So the way I always do review sessions is you ask questions, I do answers, work as many problems until we run out of time, or until we run out of questions, whichever comes first. So what questions do we have? Ooh, a purple pen.
So last night I was working on homework 4.
Okay.
And realized that I didn't really understand the encoder decoder as much as I thought I did.
Okay.
So I'm trying to figure out how we work through like designing like binary to gray code or something, just so I can understand the process of how.
Of an encoder decoder type problem? Sure. Got a preference on a code?
I mean, can we try like binary to gray code?
Binary to gray. 3 bits, okay? All right, so first off, it's always good to have your codes. That's binary. I'm going to put gray over here, because then we could do our decoders in between. Okay, so that's binary to gray. Now, when you put up your pair, the decoder to the encoder, they're always done binary style, position-wise at least.
What does that mean? What do you mean by binary?
They're written in that order. That's what I mean by that. So when you find, because they're usually positioned around, and they'll give you a number. And traditionally, we write the number in decimal because that's just easier for us. But when they give you a number, the number they gave you in decimal was they interpreted the binary pattern as if it was going to be a binary pattern. So you have your binary number coming in, which is 3 bits. And you're going to have a priority encoder over here, which is going to give you your gray code number, and it'll be in 3 bits. Exactly. Because that's how the people created it. What you do is you say, well, who cares? That's just a number they wrote on the plastic on the outside or on their labels. Who really cares what number code they do? Right? What this one is going to do is if you activate this line, it'll send the code 000 out. Right? So all you have to do is match the patterns. That's what makes this kind of a quick, easy style, is just match the patterns. I just go, well, 000 does want to go to 000. So if this code was 000, that code has to be 000. If this code is 001, that one has to be 001. You start hitting your difference here. When 010 comes in, the code I want to output is 011 on the other side. So I just hook them diagonally across. All right? Such that somebody sent me in this code, right? This code comes in, it activates this line. Everybody else is deactivated. It'll activate this line, so it'll send out 011. When I do 0, 1, 1, it's got to go over to 0, 1, 0. So they cross. It really is that easy. All right? 1, 0, 0. I mean, it'll get kind of complicated in the things that go across, but 1, 0, 0 goes to 1, 1, 0. All right? And it's just, what code are you coming from, and which one are you going to? This is the from side, and this is the to side.
And some of my friends had problems in the homework that were like not to grade code but to yeah. And I didn't understand what that was.
There's like a bajillion codes. And the whole point of that was I was just giving you lots of different codes that are in the book that they reference, right? So they're in the book, but it's irrelevant, right? I mean, I could make up Larry code, right? And Larry code could have whatever binary patterns I want to them. You just match the patterns.
Yeah.
It's totally irrelevant, right? So they have lots of different codes that are out there, right? There's, you're probably thinking 2421 as a code. 2421 is a code that's, it's a BCD style code. It only does decimal numbers inside there. But what it's designed to do is it is a code that automatically is self-complementing, which what we mean by that, so remember we calculate the complements and we talked about the ones complement, the twos complement, but we said that's true for any base, so there's also like a nines complement, a tens complement. 2421 code is such that if you flip every bit, you get the nines complement. So they wrote that code as a version of BCD that would allow you to easily get the nines complement, then you add 1 to get the tens. Yep. So, I mean, that's why it's there. There are just tons of these codes that are out there. The book had lots and lots of them in there. And I said, hey, look, I'm not going to emphasize them because you can look them up anytime you want, right? You get a new weird code, Google the dumb thing, right? Google will give you a plenty good coverage of what that code is and why that code's history was there, right? Because all we really care about that is the bit pattern. So it's irrelevant. It's just a way to specify a bit pattern to try.
So will we be converting to grade code on the test? And like converting to any codes? Do we like know right how to do that?
Well, I could have you convert to any code I want, right? On a test, I mean, I wouldn't expect you to memorize all these different codes. So.
Which codes would we want to have written down in our notes? Like,
If it's beyond the standard codes I've covered in class,
okay.
right, then I would give you the code.
So we need like gray code.
You should have like gray code and binary, but really you should know how to do ones and twos complement, but I want to write those down. I mean, those ones you ought to be able to figure out pretty quick and easy. BCD, we've done a ton with BCD. That's about it. Anything else, I'm going to give you the code. I don't believe in stupid memorization. It's worthless, right? Anything you can search on the internet and get well, I don't feel is a good use of your brain power. Right? What I do want is I want you to understand the ideas of how to do them. That's important because once you got the codes, you have to know the idea. If you know the idea, you'll blow through it.
How would you suggest like studying so that we're like best prepared for the designing? Like if you ask a design question?
Yeah. It's guaranteed. I'm going to have to ask some design question. In all likelihood, I usually ask anywhere from, usually it's like 4 or 5 problems is typical on the actual test. So I had told you the practice is always going to be longer because it's just always better if the practice exam, you're like, right? And then you get on the test and you're like, oh, okay, I got this. That combo always seems to work better. So, the only thing that really works for good design stuff is to do design problems and make sure you understand the idea. So that's why I also try to give you a bunch of different types of problems on the practice. the homework stuff and the practice exam things, those are going to be it. If there's any particular design styles, right? So we have some basic design styles that are out there. I'd be very familiar with K-maps because K-map is like our sledgehammer. K-map always works. It always does a pretty good job, right? It's pretty safe to put down whether it's into a circuit or whether you're going to put it into programming. It's usually pretty safe. You do a K-map, you're probably okay. Right? So that's kind of the universal, your fallback, wham, I could do this. Okay? Even if I specifically ask you for a different problem and you're like, oh my gosh, I don't remember how to do that one. You won't get full credit, but if you do some other technique and you at least solve the thing, I can give you partial credit for it. Now, it's better to know all the techniques so you can do whichever one's there, but I mean, if you get to a point and you're like panicked, right, you are much better off doing something and getting an answer than getting nothing. So that would be the other thing I'd do. And think of this in real life, right? If you got a job and they're like, hey, we need something here to do this, if you're not, it's a rush job, you're working quick, you don't remember the particular technique, having a functional technique is better than having nothing. So, it's always a good idea to be able to produce a functional design. But beyond that, you've got your K-maps, we've talked about MUX design, we've talked about decoder design, we've talked about encoder decoder that we've done. You mentioned you could do things like let's say like a logic. I'm always a little bit reticent to say that, but you could do a logic to prove the two things are similar. I would probably never ask you to do an actual logic design problem itself. Some people think they're really important, but you will never do this in real life. Showing two things are equivalent, I'm totally cool with that. But just it's never a good idea to design like that. You could do a hierarchical design where I give you something, hey, here's this type of unit, build them together to combine something. We did that with, half adders to make a full adder, that type of stuff. You can technically even just write out a truth table and just read them off. Sometimes they're in a pattern you recognize. So we've done that one too when it's a small design, like 2 inputs or so, and you can just recognize, oh, that's an AND gate, or oh, that's an OR gate, that type of stuff. So I would just keep those kind of basic techniques in my head and see which one seems to be the easiest or which one is asked. Now, that's kind of some general overall guidance. If there's a particular problem type we want to work on, sorry, these things never seem to fit comfy. And as you talk, it's like fogs into your eyes. If there's a particular type you want to talk over, I'm more than happy to work a problem or something as a demo.
Can we talk about the MUX design? I know you had problems on your practice test.
Yeah. How big a MUX design do you want?
Could we do this problem from the midterm B?
If you want to.
Okay. It says, what is the MUX design for, and then it has this search, if you want to look at it, instead of me reading it off, it's the last question on there.
Oh, okay, that's because I'm trying to be a pain and make you convert stuff. So this is one where I can make you do logic, is I give you an ugly statement, and then you have to figure out what the truth table is and everything for it. Because to do a MUX design, you have to have a truth table. So one way this allows me to kind of double dip. So just break it down to 2 stages. Step number 1, find something really easy to put into a truth table. One of the easiest things you could do is just always go to sum of products. Right? If you reduce it down to a simple sum of product type of statement, it's pretty easy to then write it into a truth table. So that would be my first step. So we walk through and we distribute. B and B prime is 0, it goes away. And then B with this gives me A prime, B, C. And now I've got this one, but this is De Morgan's, right? Because I got the prime outside, so the only way I can expand that is to do De Morgan's. So I get B prime or C prime, and then I have to distribute. That one stays by itself, or A, B prime, or A, C prime. Then I go and make my truth table. Now, what sometimes helps when you're doing mux design is to reduce some of these. So if I actually, notice these are both repeats, right? Both 0, 0. Here they're both 0, 1. I've grouped them up by 2s for this reason. And the reason why I do that is the mux design goes at it 2 at a time and grabs them. And the way we do mux design, the basic mux design type is always to grab everything but the last one. Now, technically speaking, you could do it any way you want because you can reshuffle the rows. So without loss of generality, you shuffle it to the row you want is on the right-hand side, and then we'll take it from there. I didn't grab a name for this, so I'm going to put F. And then I just walk through. This tells me where the ones are. So I can kind of consider this in my numeric format, right? This is 0, 1, 1. And this is 1, and it's 0 because it's primed, and we have no C's, so it's X. And then this one is 1, and we have X because we have no B, and a 0. So I just walk through, and in any of those number patterns, I put them in. So 0, 1, 1, right, 0, 1, 1, that's here. 1, 0, X, so that's 1, 0, both of them. And that's a 1. And then 1, X, 0. So that's wherever it's a 1 and a 0, we got that 1, 1, and a 0. So that just marks those all in. Everything else is a 0. Then with mux design, you just walk down every 2, and what you're going to write is either 0, 1, C, or C prime. And it's whatever the pattern you see. They're both zeros, so I write a 0. It's 0, 1, that's the same as C is. Since it matches, this is C. They're both 1, so we write 1. This one is 1, 0. It's the opposite of C, so it's C prime. You just walk down and fill them out. I'm basically done now. I just draw the circuit. Oops. It helps if I don't draw it backwards, though. Dyslexia strikes again. All right, so I have 4 groups, 0, 1, 2, 3. Out here comes F. My patterns for these are 0, C, 1, C prime, 0, 1, 0, C, never trust my memory, 1, C prime. And then the address selector is AB. The address is always telling me what this part is. And that's AB, and that was what kind of grouped up my little C patterns the way they were. Done. And I could say, hey, build this in Verilog. And I'd be like, sure, no problem. I'd say module, and whatever we want to call this, mux f for mux function or whatever. And I've got an input, and I'm going to put A, B, and C as separate little inputs. Since they're all the same size, I just made them all wires. I can just put them all on the same line. There's no biggie to that. And then I have an output F. All right, then, now since it's a little bit easier to write, this is a big one, right? And larger ones are easier in case statements. So I'm going to make this a reg, because it's easier to write it as code. I don't need any internal wires or anything else, so I can get right into the good stuff with an always. So always at star, that means the at star just tells you it's a combinational circuit. There's no memory. So always at star. All I need for this is a case statement to build that single mux. So it's going to be one line, so I don't need a begin end. Case statement requires the thing you're doing the case on, which in this case is whatever your address is down here, which is A and B. Then I've got my 4 cases, which are what's labeled here. I got to pick one of them as default. Right? If nothing else is told to me, and I really know nothing, it's just a test problem, I generically pick the last one because then I can just wait to the end and hit default. Now, in a real design, that's probably not the truth. Almost always in a real design, you want the default to typically be like 0. Because it's what do you want it to go to if everything else, like things go wrong, things aren't working right, somebody hits the reset button. When they hit that reset button, something weird's going to happen. Where do you want it to go back to? It's often 0 because that's usually your starting state. So typically it's actually a little bit better to do the other. But as long as you're aware of that, for simple test problems, if we don't specify, who cares? When we get to memory, it'll start mattering. So I just kind of put that out there as a think about it area. All right, so 0. And all I'm going to do, right, you put the colon to specify what do I do when 0 is hit. It's going to do a comparison. This is a 32-bit number, interpreted as a decimal. It will truncate it, so it'll be totally fine. If you wanted to be really nice to specify exactly what you meant here, I could also come in and say 2 bits binary 0, 0. That would also be okay. If there were several that did the same thing, I could comma separate them. So that's also a time saver if you need them. All right, 2 bits binary 0, and then I say, well, what happens? Well, F is going to get the value that's on line 0, which is 0, which in our case is just 1 bit of 0. All right, because that's what this says. This is the 0 here, and 0 gets routed to F. Yay, we go to the next one. 2 bits binary 0, 1. Put my colon, and F gets the value of C if it's 1. There we go. For 2 bits binary 1, 0, F gets the value of 1. And for my last one, default. F gets the value of C prime. I am now done, so I say end case. I do not need an end for the always because I had no begin for the always, but I do need to end the module. And I'm done.
So do we need to know how to write out code on paper for the test?
If you're doing it, yeah, because I'm not going to give you a computer.
No, but
Yeah.
being able to write parallel code is part of the test.
Small things like this, we've done them on the board a ton. I feel totally safe with short snippets of code. I'm not going to give you some big, nasty, ugly thing.
Yeah.
All right? But I could ask you something to implement a couple AND gates or assign a function to something, right? I mean, a small snippet of Verilog code well within your reach. All right? And all of these there's always this kind of simple thing. What's being passed to me? So you could just look at this and say, well, what's being passed to me? All right? If you look at the truth table, here's my inputs and here's my outputs. All right? You could look at a picture and say, well, 0 and 1 I don't need to pass. I've got those. Other things I need is C and AB. That's an input, and what am I producing? It's F. So it's easy to look at the pictures and figure out what that is. So this section's very simple to write. And then, all you have to remember is, am I going to put this inside an always? If so, it's a reg. And if it's not inside an always, then don't put reg. That's really the whole difference as far as we're concerned. Because anything else, assign or anything else, just wants the wire version, which you get by putting nothing. If it's mux that's size 2, it's easy to do with the question colon syntax. If it's anything beyond that, it's easier in a case statement.
On the truth table, why did you just use like C on that? Like when you were like putting 0?
What, here?
Yeah.
Right? Well, because the design technique for this is we split our input where we break off the last one. Whoever is the rightmost becomes their own little thing, and that's going to be one of our deciders. And everything else is an address. So that's kind of just a convention. We just agree we're going to do that. And the reason we need to do that is we want to group our outputs by 2s. And so I'll have the ones that are both similar. That's easy, 0 and 1. But what do I do when they're split? How do I tell the difference between these two? And we just noticed that this is identical to C in that position. And this is the reverse of C, which is C prime. So that's why we needed that extra variable, because it could determine what's going on there. That also then meant I had one less address bit, which means it's half the size of a mux. So that's why we, functionally it allows me to half the size of the device I'm working with, which is always good. It's less code to write, a smaller device to use, so on and so forth. So it's just kind of helpful. But then we just notice, hey, the pattern's the same. So we always break it down into 0, 1, whatever the last variable is, and whatever the last variable is prime. And then you just compare them. If they're the same, it's either 0 or 1, and then you just compare these. 0, 1, identical, it's C. 1, 0, it's flip, so it's C prime. And that's really all there is to it. Does that make sense? We could have had anything. I mean, if this had been 1, 0 here, then I would have had another C prime. You just, wherever you go in, you just find whatever the pattern is in that block of 2. You ignore everything else, because the mux will cut everything else off. So it just isolates that term for you. I'll put it back where it was. And the reason why I picked this one on the practice exam was it basically gave you every pattern. All right, so I just wanted you to make sure you knew what each one came from. So on a small scale, there's only so many permutations. I'm not obligated to do that on a test, but on a practice exam, I want to make sure you saw all of them. Feel good with mux? Awesome. What else do we want to talk about? Yeah. Oh, sorry. I saw her hand. No worries.
Question 5 on the practice test, we had some code for the delivery we had to implement. So what I did was doing a sign statement, but that's not the solution that you had.
Oh, there's tons of solutions.
Okay.
Right? As long as yours is equivalent, I don't care. Right? To write up every possible one, right, there is not that much paper in the universe. I mean, it would really just blow up. So all I had to do was give you something that you could look at. But you're under no obligation to do it exactly the same way. And a sign statement is actually probably easier. The only reason you might have to do a particular thing is if I said, build it with individual gates, right? So if I told you, build it with individual gates, you should build it with individual gates. If you give me an equivalent thing, you'll lose some points, but you'll get something as long as it's a true design. If you give me nothing, you get nothing. So, the more you give me, the more credit I can give you. And that's basically how that works on my area. But you can just look and see, does your assign statement do the equivalent? And if I don't specify and yours is less time, then bully for you. All right. On generic ones like that, I tend to do the gates, even though it's more tedious. And the reason I do that is I found it's easier for most people to track and check to see that there's equivalent, because they can just walk through and go and some people struggle with a really big assign statement reading it. So even though I personally think the assign statement is a better way to do it, for people checking their work against it, it's sometimes harder.
Thanks.
You're welcome. Yeah.
Okay, really like the same thing. Could we go through making it with the assigned statements?
You would have to tell me the problem, because there is nowhere in this plan I memorized that. Well, if you tell me what problem you want me to write up here, I am happy to solve whatever problem you want me to write.
So the equation we had, like, that got down to was C prime D prime or B C prime.
C prime, D prime, or B, C prime?
Yep. Or A D prime.
Awesome. And I'm presuming this is equal to some function f? Awesome. All right. Now, when you're looking at this, do we want to do this with an assign statement? Do we want to do this with gates?
Do it one of each way.
Do it both ways. Sure. So the assign statement is really easy because I don't need any intermediate variables. So that's one of many great things. Actually, let me just put, I'm going to put a generic thing, module, this function. And we need to pass in input A, B, C, D, output F. And then end module. Because I'm presuming you want a circuit and code and everything. So my statement is where I put this kind of three little lines here, that's where you would stick whichever of the two things that we're in that you're deciding to do. That way I don't have to write this both times. So whichever way you decide to do, like when we do the assign statement, you would just stick the assign statement in there.
This is like a choose your own adventure novel.
It is, right? Those things actually, they came out when I was young. It's kind of like D&D's or TSR's attempt to stay in business. That actually kept them afloat for a while. But yeah, so yes, this is very much that kind of insert your own novel. So the three things could be equal to, all right, so we want an assign. So we'd say assign, because remember, assign is a way that we're saying build a thing that's going to implement this circuit for me. And it just does a quick one-liner type of a build. And I want F to be equal to, and all I'm going to do is convert this. And we just remember that whenever we see a prime, prime is going to become a tilde. And the and, which is kind of a dot, the not written thing, dot is going to become the ampersand, and or is going to become vertical pipe. Oh, sorry. That's just our equivalents into Verilog. Right, these are the bitwise versions. Remember, there are the logicals. Does it matter which one I do here? No, it's a one-bit thing. There's absolutely no difference on a single bit between bitwise and logical. The reason why I tend to do bitwise as a general rule is it's telling people that I'm trying to just do, you only do bitwise when you're doing manipulations for gates and things of that sort. So it's kind of like a note to other designers. Whereas a logical, if you were doing it, you do logicals when you're doing test cases and code and things like that because you're trying to test a particular value and there's really only one thing that's going on there. So it tends to make people think that this is a code or an algorithm that's running as opposed to one that's been built. So it's not that there's anything magical that it makes it do that. It's just more what it causes human beings to think. And that's really more the reason I'm going to pick this side. But I would note to you that there is absolutely nothing technically wrong with the other side. Okay, so F. I need not C and not D or B and not C or A and not D. Done.
You have no parentheses, even though order of operations doesn't require it?
If it makes you happy. So I tend to hate parentheses unless I absolutely need them. And the reason is I just find it's really hard to follow once you start getting parentheses in there. And if you look, this is kind of a track. I heard some people talk about jobs and things like this. So I'll give you a commentary. Having worked in industry and actually done hiring in industry, and I do most of the hiring or the hiring chair for our department. So I look through tons of resumes and everything else like this. I could just tell you right now, if you do things like lines on your thing and whatever, it's going to draw people's eye to that and it draws it away from the important information. What you want more than lines is you want blank space. So if I walk through and I did a whole bunch of this, is that more readable to you? Now imagine if I did this. Is that more readable? All right, the blank space strategically around the ors buys you a lot, doesn't it? This would be my actual recommendation. Empty space causes, your eye wants to naturally go to those letters, right? You're going to group naturally to whatever is darkest on the page, and you really like, your brain likes line patterns. It just does. So what you want to do, you give it lots of lines, and your brain has trouble focusing which line matters. That's why parentheses confuse people. But blank space just creates empty area, and your brain just goes, that's irrelevant. And that's true. So you put the irrelevance where it's irrelevant, and then it'll cause your brain to naturally jump to the right area. And so that's why I always say blank space is actually more useful, not only here, but it's actually useful inside when you're doing your resumes and everything else. Put blank space around the things you really care about. And what's going to happen is it's going to cause those areas to jump out at the human brain, and they'll read that. And so there's a couple basic things, what I call real estate on your paper rules in those areas that really make certain features stand out, and I suggest you rearrange it slightly for each place you apply to. And it'll cause the things you want them to think about you to be in the areas. Upper left-hand corner is really, really important because people always start reading there, and people get bored. Have you ever started reading something, get part of it, like, this is boring? Right? You don't want that slump in attention during an important feature of you. So you put the most important features of you start of the paragraph. Now, if you see something that resonates and you're like, ooh, I'm looking for that, all of a sudden your brain is now focused and you'll read further. So people just tend to lose focus quickly. You've got to put the things they care about. So if you pick those upper left corners, put blank space around it so it causes them to focus on your text, and make the things in those upper left corners be whatever it says in their job advertisement. Right, so you find their job advertisement and you put their keywords, right, in that area, in that upper left area. They go, ooh, this person matches, right? Trust me, you just want to be done this job when you're hiring somebody else because you got your own jobs to do. Okay? So you find somebody who is like, boom, they hit all the things. It's like, woo, I can go home now, right? I can get back to my regularly scheduled life that they're not giving me any extra slack time for. So make it easy on them by kind of playing the same game, and you make it that much more likely you're going to get hired and not the other person. Okay, we good? We want to do this with what? Individual gates, with code. What do we want?
Individual gates.
Okay. So it could also, so this is option 1, option 2. We could build it with gates. Now to do these, this is going to be a gate, that's going to be a gate, that's going to be a gate. I need a wire out of them into the OR. So I'm going to need 3 intermediate wires. Let's see, we A, B, C, D, whatever. I'm going to call them wire E0, E1, E2. Fair? Okay. First I need, and I also need some NOT gates also, because I have to have the outputs of these. Let's see. I need NOT C and NOT D. Looks like that's all I need. Because I need the output of these NOTs. All right. First, I'm going to build my NOT gates. The output will be NC, not C, and the input is C. And NOT D, output's ND, input is D, which I think was capitalized actually. By using the comma, I could just keep adding more of the same type. Just saves you having to write a whole bunch of them. Nothing wrong if you put a semicolon into another NOT, though. I'm going to do my AND gate. Or actually, 3 of my AND gates. So I'm going to call this one AND0, AND1, AND2. AND0, I'm going to output to E0. And the inputs are NOT C and NOT D. And 1 will output to E1, and it gets B and NOT C. And then I've got AND 2, which will go to E2, and it wanted A and not D. That was the last of my AND gates. And now I've got one great big OR gate. All right, my OR gate. The output is F, and the input is E0, E1, E2. And I would shove that whole thing in there.
it be a register if you're doing a sign statement?
So assigned statements will not allow registers. All right? Registers only if it's an always or an initial. It's the only two cases you ever want regis.
Is that bottom line say or, not X or?
It says or, my or.
Oh, okay.
Sorry, yeah, bad handwriting. You just have to give it some name. Now, according to the Verilog actual system requirements, you don't have to give a name. It's supposed to give its own name. And depending on the particular implementation you have, they will give it their own names. The problem is Vivado sometimes gives it a name and sometimes leaves it blank, and you get a bunch of things that are called blank, and it creates problems. Then when it tries to reference them, it throws a hiccup. And sometimes it'll simulate, and sometimes it won't. And you just don't know when it will and when it won't. So I'm being like really pedantic about saying always put a name, just because I don't want you to run into Vivado problems. And like I said, Vivado they've got a huge chunk of the market. So they're probably somewhere around 70+% is owned by Xilinx, right? Because their stuff, they got in early, they have really great hardware. They are not a software company, so they hired a separate software company that's not a hardware company. And so, they've got, the code runs pretty well, but there's some kind of like hardware-oriented features that are not always there because the company they hired was a software company. But they're not going to give their proprietary stuff out to another hardware company, and they did try to write their own, and it was really buggy. So, yeah. Yeah.
So I'm on the one on midterm practice yesterday.
Okay.
I didn't convert correctly to ACST. Yes.
Ah.
Wait, what? Yeah, I'm sorry. So the number 89.82825. Oh wait, no, I converted it wrong.
Yeah, because I was saying there's no, yeah. Okay, so 89.81218.
828128.
Is that correct?
828125.
82125?
828.
828,125.
Right. I converted
Okay.
it to a text incorrectly. We just got to
Okay, so we need to get binary first out of this. Actually, let me erase this side because we haven't used this one more recently, because that looks like it's going to be big. I could be wrong, but I usually try to make these so they terminate. And that ending 125 suggests that it probably will terminate, but you never know. All right. So we're going to separate it. 89. And we're going to do this one by the divide by 2s. You could also do divide by 16s, but I tend to find I do a much better job divide by 2. And 8, 2, 8, 1, 2, 5. All right, let's do this side. So 89 divided by 2 gives me 44, carry a 1. That gives me 22. Carry nothing. 11, carry nothing. 5, carry a 1. Gives me 2, carry a 1. 1, carry nothing. 0, carry 1. Okay. All right, this one. So let's see. That gives me, start doubling, that gives me a 2, 5, 6, carry a 1. That'll give me a 3, times 2, 5.
Will we have a calculator on the test?
No. Why would you need a calculator? I would probably not give you a number this big on the test, but you could still do them when it goes through. It would be probably smaller, but I will tell you this, that I probably wouldn't go beyond like 4 digits on a test one. But if there's calculators in there, calculators become a difference of who has the best calculator. It doesn't really say you know how to do it, because calculators, you don't even have to do this method here. Calculators, you could just type in a number and say convert to binary if you have the right one. So now it comes into who has the best calculator. That's not a good test of your knowledge. So that's why I don't like calculators on the test, because it doesn't test can you set the problem up. And if we're doing this, why do you think I want you to do this step? I mean, because you will in real life have a calculator and you could just say convert, right? But what happens if you have to build a circuit that does the conversion? Somebody types in a number on a keyboard and you have to convert it. And there's nothing to convert it for you. You're building the hardware to convert it. Now what do you do? Right? That's when, if you know the methodology of how to do it, just like we did with everything else, we can say, oh, I'm going to build a circuit that's going to do what I do. And we break into each one of these and we go, oh, this is, for instance, multiplication. And we talked about in class how I could build a simple multiplier. But multiply by 2, that's a shift circuit. So I can just start shifting digits and stuff like that. This becomes a much easier situation. Okay? So I want you to know the things. So if you ever have to build the circuit, you can build the circuit. And you understand how that conversion went and why it works. Once you get comfortable, I fully expect you're going to type it in a calculator and say, convert it for me. Okay? But on the early stages, you want to make sure you understand the whys. Once you have the whys, everything else falls in line and you can use stuff simply. All right, we get to double again. So that becomes, 2, 5 becomes a 5, 6, I get 2, carry a 1, the 1 comes down. That carries a 1, so that's going to give me 1, 3. Yeah, I don't think this, it might end. Let's see, and then we are going to take this one and double. 1, 2, 5, that becomes a 2, 5, 3 becomes a 6. It does end nicely. 2, 5 becomes a 5, 6 becomes 1, 2, and then I get 0, 5, 1, 0. It ended nicely. I usually do try this to make sure it ends nicely, but all right. So we then come and we just read it around in order. 1, 0, 1, 1, 0, 0, 1. I see a dot. 1, 1, 0, 1, 0, 1. That's in binary. Now to go to hex, I start at the point, and hex is 1 nibble, or 4 bits at a time. I need 4. I can always add nothing to the outside. I grab this way, again, starting right at the radix point. I need 4. I can always add nothing here. Adding zeros on the end, either left or right, doesn't change anything, because I'm just saying add 0 of this digit and 0 of this digit. On the outside edge, it's not shifting anything over, so it's not changing anything. So far, so good. Then I just read them as an individual digit. This is the number 5. That is the number 9, radix point. This is 13, which 13 is D, and that's 4.
Okay, the answer key?
Yes.
59.DA. So I got that answer.
It's possible that I misdivided somewhere here or mismultiplied. Does it? People can check my number. Is the, what's that?
I got the same thing as you.
That's what I got here?
Yeah.
That means there's a problem on the answer key. Yeah. Because it's possible when I read that one too that I just skipped off the 0 here when I wrote it down. And skipping a 0, because I'm reading them fast and doing them late at night, and I did this several years ago. And I just look through and see, is that type of problem good? I go, yeah, conversion, we need a conversion problem. So I never look at them again. So unless somebody tells me there's an error, I don't know that there's an error. But I will have to fix that one. So it says D8. Yeah, and all that would be is this one shifts over.
It's
DA. Boy, I'm not even sure why I got DA, because DA would, for an A, it would be 1, 0, 1, 0. Is it like typed, or is it a printed thing that was scanned?
I misread it.
I thought it said 4, but I'm not.
Because I'll admit, if it's a handwritten one that was scanned, right, and I wrote my A and I kind of did it kind of fast, right, A and 4 can look like each other, particularly if this kind of comes in, right? So, and if I kind of went, right, that could start looking like an A. And I'll admit my handwriting is terrible. So if it's a handwritten thing, I would totally buy that goes in. Like if it was 8, I could see how I could do that. I just missed a 0 copying. It would be really hard to get to A because I would need a 1, 0, 1, 0. That's a very hard. I mean, I guess I could have shifted that whole thing over 1.
It definitely says 4. I just.
Oh, okay.
I don't know.
No, that's totally cool. And like I said, I could see them being similar, and I could totally see myself making a typo. And this is why I always say do a check. Have a check some other manner, because it is so easy. I don't care how, whatever we think about ourselves, the reality is nobody is perfect, right? We had one perfect person. He came and died on a cross. After that, all the rest of us are mess ups. So, and that's partially why I want you to just build as many routines in your mind to double check yourself, right? Because we will all make mistakes. So don't sweat it, all right? And on a thing like that, like if you had all the work done and I notice one little problem, I don't mark off much for some little mistake, right? If your mistake was partway through here, you shifted something wrong or whatever, particularly like if you multiplied wrong on something like that, I'm not going to take off much for that at all. It's not relevant to me, but it's something. So I usually take like a point off out of 100 for the whole test. It's not a biggie for that parts of it. It's much bigger if you just clearly don't know how to do the operation between here, because that's what I care about. Yeah. I will just note this also as a thing. I have also had people at the end when they do their check and they're out of time and they go, I know there's something wrong here because I did this check, and that will never hurt you, right? If you're actually right. I mean, if your answer was correct and you said, I know something's wrong, then that's going to make me start to wonder about you. But if you were actually wrong and you're like, hey, I did this check and I'm out of time, but here is what I would do to go to check my area, and you give me a reasonable approach to it, I will give you partial points back for whatever mistakes you made. Because I believe at that point, you're trying to convince me if you went into a job that you would know how to handle that. And if you saw a problem there and you give me a reasonable direction and you need another 30 minutes to fix it, you got your 30 minutes, right? So I can then believe, okay, it's much more likely you'll get there. So give me whatever you can to let me know that you're going to get there and we're good. All right. Yes?
I'm sorry. So on number 4 in practice test A, I'm just a little confused about the theories and how you want us. Okay. I just don't know when you're asking if the it has an even or odd parity, and then the third example has both. How do you want us to denote that?
Okay, so that particular problem there was designed as kind of like a fun, I remember this, I actually invented that one about 10 years ago. Because at the time people were asking, well, if I just looked at codes and it didn't say anything, say they were, because I had a group of people who were going to one of those security hacking tests that's out there, you might hear like Hackfest, stuff like that, and they're asking, how can I just look at a code and get some idea of what type of code it could be? And so for instance, if it's ASCII, it'll either be all even parity or all odd parity. It can't be a mixture of them. So you could actually kind of exclude some stuff out by saying, oh, you know, I recognize that there's a mixture of them. And it made a fun way to kind of test people on it. So I then stuck that into there. And it's kind of stuck ever since because it's as good a way as anything else of being able to recognize it. So that was just, if nobody tells you what it is, can you make a guess at what the code might be? And there actually is quite a bit of motivation for that type of skill set outside reverse engineering and so on. So if we want to talk on a problem using ASCII and parity, I have to have numbers, or I can make them up. But what do we want?
Well, the only one that was kind of, it was 0, 0. Okay. Yes, 0, 0, 1, 0, 0, 1, 1, 1. 0, 1, 0, 0, 1, 0, 0.
Is that correct? All right. So I'm going to group them into groups of 4. Because that just makes my life easier. Now the first thing I can do, this could be ASCII, these could just be regular numbers, it could be all kinds of different stuff. ASCII is 7 bits, and then there's that extra bit. So it could be a parity bit, it could be an extended ASCII, there's lots of possibilities. But let's say, for instance, I want to check parity bits. So I would get 2 nibbles at a time, 1 byte, and I would see how many ones. So here I've got 1, 2, 3, 4. So this is even, because there's 4 ones. And this one has 1, 2, 3. This is odd. So I know this is not ASCII with either parity because I can't have a mixture of even and odd parity. It's either all even parity or all odd parity. So if I gave you some options where I said, you know, hey, this could be, you know, I know it's one of these 3 things. It's either ASCII with even parity, ASCII with odd parity, or it's hexadecimal bits. Then you would say, well, it's not ASCII with even or odd because it's a mix. Therefore, the only option left would have to be the hexadecimal, you know, coming 1 block at a time, and I'd read it as hex, right? Or whatever I say. If I give you options, that's what it would be. If I don't give you options, all you could say is it's not ASCII with even or odd parity because it's a mixed. Now, I mean, that's as far as that one would go with this, right? I've just identified it as not one of those. If that makes something unique out of the list of possibilities, I don't know what possibilities I gave you in the problem, because I honestly don't remember it.
It would just convert to BCD or...
Okay, so BCD. So BCD I could also check and make sure that the digits make sense, right? So then I would walk 2 at a time. Since I know it's not one of those, I'm hoping it's BCD. Well, this is the number 2, and that's the number 7, and that's 4, and that's 9. And you could rule out some BCDs, right? Because if it was the pattern for 10, through 15, I know that's not a BCD thing. So that would give me some patterns I could cut out also. Don't feel sorry, otherwise I'm just standing here and drinking my tea, so.
Okay, on number 7 on practice test, when you were building the always, you used less than or equal to instead of just equals.
For which one? Oh, inside? Yeah.
Yeah, exactly.
So I've been mentioning there's 2 types of assignments that are done inside and always. Right? So there's what's called blocking assignments and non-blocking. Blocking is just an equal. Non-blocking is done like a less than equal, but think of it like an arrow, a really bold arrow. It's just saying to do an assignment. Now, there are some subtle differences. On a cursory level, they both assign. So in that sense, they're the same. But the difference comes down to some areas like when there's multiple ones. So let's say I had appropriately defined stuff and I had C equals, actually let me do it this way, B equals A, C equals B. All right, this is in blocking, and assume they're registers because this would have to be inside and always and everything. Because you can only do these inside either an always or initial. It's the only spots you can ever do either of these. Outside, non-blocking is not permitted because it doesn't make any sense. In an assign statement, you can only assign one thing. So what does it mean to assign block or not block? There's only one thing. You're never doing things either blocking or non-blocking. Think of them as sequential and parallel. That's really the difference here. So let's say A is initially 5 and B is initially 7 and C is initially 2. Fair enough, just as kind of starting conditions. Now if I walk through this says B gets the value of A. And then C gets the value of B. So I walk through, just exactly what you would expect in a regular programming language. Everybody has 5. Now we take a look at the same exact scenario with non-blocking. And initially, A is 5, B is 7, C is 2. Same situation. The way it implements this is it stops time. Right? And it just says, everything in here I'm going to do simultaneously. So this is the previous time, and this is the next time. And it just kind of holds a temporary variable, and then it assigns them all at once. So it says that my new B is going to become A's value, which is 5. And my new C has become B's current variable, which is 7. So it goes through and it calculates everything in parallel, as if they happened exactly at the same time. And then it says, great, I figured that. Move the time instance and so I get 5, 5, 7. Do we see the difference? So in this case, this is the difference between blocking and non-blocking. Now the question is, well, first off, why would they ever do such a strange thing? Well, circuits are parallel. So now you got to answer the question, why would you ever assume they would kind of follow in sequence? And the answer to that one is actually, you would assume they follow in sequence not because you'd assume a circuit follows in sequence, but because you want to write code in sequence and for it to guess a circuit that is equivalent to that. Appropriate length of the wires, whatever else, to time it correctly. And you're depending upon them to build you a circuit that actually does that. That's why you would do that. Okay? But it comes down to kind of how do you pick them? All right? Now, then you have to ask, well, which one should I do in a given situation? And I've been telling you so far to do everything with blocking. And the reason why I've been saying do everything with blocking is it turns out when you're doing things with no memory, you want blocking. It's safer. And once you get to memory, timing has to be done inside the memory units, not inside the combinational design. So for any of the circuits that are going to have memory in them, the memory parts have to be non-blocking. So just think of this. This is for really the memory parts, and this one is no memory or combinational. That means since it's combinational, if you're in an always at star, you should do blocking. When you get to memory, you'll have a different version. We'll have an always at, and we'll mention either a pos edge or a neg edge of a clock. When you get edges of a clock, you're in memory, and you really must do it non-blocking to prevent errors. That will start Friday. We'll start talking about memory. So we're close enough. Now, depending on the particular time instance when things happened, sometimes there was blocking and non-blocking. And early on, they said, you should introduce people to both right at the very start. And so I'm like, okay, I'll do it. And so there are some problems that have non-blocking earlier on. But the reality is there are times when that's safe, and there's times when it's not. And if you do combinational always with blocking, you're pretty much safe all the time. And if you do the memory ones with non-blocking, you're pretty much safe all the time. And you want to just completely separate your combinational and your memory units. And if you do that and you follow this general rule, you will be completely safe. And so people used to have a lot more complicated rules, and then I just noted, hey, I can cut through all those really weird, complicated rules if I make this simplification. And then you're pretty much safe. So that's what I teach, because that way you don't have to remember all these weird, when does simulation time segments start, and I can kick commentary about time segments inside the simulation, the running of Verilog, till when you get to advanced classes, so you can understand why it's doing what it's doing. There's actually 16 time instances that happen for every single time period, whatever the time period is. And it has to go through all these phases, and it does different things to accomplish what you do. But I think that's too much to learn at this point. So that's why if you see any of those right now, just ignore them. Right? Once you get to memory, starting Friday, we'll get into this much more heavy. But I used to emphasize it heavier because that was the standard. And then they still say that, but I just think they're wrong. So I do it the way I think is right. I figure I'm old enough and with enough experience at this point, I can overrule other people who think they know what they're doing but haven't worked in industry. So, yeah.
So, in the same question, the output is labeled E, but it's not a register, but it's in an always.
Is it? Oh man, that's a typo then.
Okay, so
Is it on the left-hand side? So just remember that you find wherever the equal, the assignment statement, right?
yeah.
And you got the left-hand side and the right-hand side.
Yes.
If it's on this side, inside an always or initial, it must be a reg. That's the rule. If it's on this side, who cares? You're reading values here, you're writing to values here, updating or changing them. If you're going to write to it, it must be a reg. inside an always or an initial. So, which one is that? Because I should fix that if it's
That is number 7 on practice test.
7 on A. Actually, can you do me a favor? Shoot me an email with that correction, and I'll verify it. If you find errors in anything I do, I will give you an extra credit point. Yes. So, well, yeah, no, if you find something I do wrong, you ought to get credit for doing it. Plus, I want you to be at the point where you can challenge anybody. Because I don't care who it is, anybody can make a mistake. I may have been doing this since the 80s, but, how often do you think I've been making mistakes? Right? I mean, human beings make mistakes. We typo things. We forget stuff. That's, this is reality. You have to know you're right and feel confident with it, but then be willing to assert yourself and say, hey, and you do it politely. You go, hey, I think this should be this. Anybody who's a decent engineer should be happy that you point out a mistake nicely. Because think about which would be better for you, that one of your friends and colleagues points out to you, hey, I think this should be this, and you fix it, or wait till it blows up in some customer's area. And everybody's like, why did this fail? Right? You don't want that. Or worse yet, it gets out to some end person using it and you discover some accident happened because of your mistake. I mean, that really feels bad. So, what we want to do is get a culture where we all feel comfortable that anybody can comment and go, hey, I think there's a mistake here. And good engineers have always had that type of a culture. And bad engineers try to protect their stuff and hide. So you just want to get to that kind of open thing. And you can see lots of examples where people fixed them. Let me give you, this is a true story. And this actually happened when I was doing some of my engineering intern things towards the end of my career. I was working for a heat treating furnace. There was a really old guy who was working there, who was just kind of working because he was retired and wanted to stay active. And he was telling me during one lunch when he worked for International, which is the big truck building company and that. And he was saying, he was working as a young engineer. They had just come out with their first all-electric truck. It tilts the cab forward. He's like, all this kinds of cool stuff. He was working late. The janitor comes through sweeping up. And so, he's like showing off his truck to the janitor because he's like all proud of it. Hey, look at this cool thing we built. And the janitor's like listening to him politely and stuff. And he goes, that's really cool. What happens when your battery dies? How do you tilt the cab forward on your electric circuit? Well, the battery dies and the engine's not running. There was no way to get into the battery to jump it. The only way to do it then was to cut a hole in the side of the truck. So he quickly realized the janitor was right and they had to do a redesign. They had their demo model built. Nobody questioned it until the janitor. Now, you could be arrogant and like, I don't want to listen to a janitor, or you could be smart and listen to the janitor, right? So the point is, it's not, degrees don't protect you, years of experience doesn't. What protects you is humility. Listen to everybody, because somebody's going to have something that's going to be useful to you. Treat them all with respect and get their input. And that saved them by finding it then. It was more expensive than if they found it earlier. But imagine what would happen if you had truckers out, stuck in some frozen area in Montana or something in the winter and somebody freezes to death because they can't jump their truck. This is going to get really bad really fast. So, his point was be humble. And, you're not all that because you get the degree, right? You should be willing to listen because you have the degree. So I passed that little bit of wisdom on from him. Right? But throughout your life, learn and stay humble. It'll really benefit you. So that's why I happily give points for these type of things.
So like the multiple choice that was on homework 3, that's also extra credit?
For the first one who gave it to me.
Okay, that was probably not me.
You were the third person who sent me a note. Yeah, but that's totally true. If you do, and I will tell you if you're the one who's the first.
Okay.
And then I go and I fix the problem because I mean, I try really hard not to make mistakes, but I mean, anybody can make mistakes. And you write out the problem and then you type it up, you know. I mean, anyway, you see mistakes in books and anything else. So that's true in labs, that's true in these things. You find something, you're the first one, boom, it's yours. All right. Okay, yeah.
So also on number 7, when you're building the always inside the case, you don't do it with like a 3-bit 000. You just put a 0.
Yeah.
And
It's still legitimate, correct, right? There's really, and I'm going to show you eventually an even nicer way than these. Whenever it sees a single 0, it automatically, at its pre-processing stage, is going to change it to this. 32 bits, decimal, and then number 0. And it'll sign extended. That's what it's going to turn 0 into. And then you only want 3 bits. Well, I've got more than enough bits. It'll truncate, and it truncates at the radix point, which is the far right. So it'll do the exact same thing. So it's legit and legal.
even on the right-hand side of the blocking.
So on the right-hand side, a 0 there, again, is going to get expanded to this. And then if I'm adding it or whatever else, it'll truncate. What's the problem? The problem can come in most notably in a few cases. If you're ever bigger than 32, anything beyond 32 is X's. So if you ever go to like a 64-bit computer, it gets a little bit dangerous and dicey. When you're passing things, right? Remember the appending trick? If I put a 0 here, right, and some whatever it is, variable X, right, and X is say a 1-bit number or something, I'm totally fine. It'll truncate or whatever, right? Appending this together, you're going to get a 33-bit number, and it'll truncate from this side, and you'll be totally cool. That won't, right? If you wanted 0 on the right and X on the left, and they're 1 bit each, this is going to be 32 bits, and when it truncates, you'll get 0, 0. It's kind of weird to be able to say it works one way and not the other, but it does. You just have to think how it expands. So then that's why I say it's just safer at first to learn to just put that. Right? Because now, if you put the 1-bit binary 0, you're totally safe. People understand exactly what you mean, and you've gotten some design intent across. Are there sometimes it's easier to read when you just put that other number in, you know, plus 0. That's really easy to read, so sometimes it makes sense to do that. It's even nicer, we'll talk about how you can define constants in the future. And that's actually a better way of going about doing it. We define set constants we want for things that have the bit patterns. And we name them something that's going to be meaningful to us. Like we can define, you know, 0 to be equal to 4 bits of 0. And then you could just use this as 4 bits of 0 after you've defined it as a constant. So those type of things, and we do this, there's a couple ways you could do this. One is parameter and the other is a defined statement. But we'll get to that later in the course. All right. All right. So I guess my shortcut of this is not necessarily wrong, but you have to check. Make sure if it truncates correctly, you're golden. So that's not a mistake. All right.
I was just wondering when to use it.
So my general rule would be to use it when you are absolutely confident that, you know, you can get away with it. So my previous school, when I was teaching, and a bunch of these examples come from there, it was in a computer science and engineering, and everybody by the time they took this course had 2 years worth of computer science. So this course was at a junior level thing when it was a very heavy computer science-y thing. So I pounded a lot more of the language theory in early because they just had a lot of language experience. And so I could make very short statements and they would understand what I meant because they had hit lots of different languages. So I was able to kind of mention a bunch of these kind of oddities of the language. And with all of you, when you're first learning it, my strong suggestion is be really pedantic at the start. Be like overly careful. Right? This is like learning a language, and instead of in English saying hi, just saying, hello, my name, right? You be very proper when you're learning it. And then once you've gotten comfortable with the language and the conjugations and everything else, then you start learning the slang. And I'm following that type of a protocol here. Now, if you have somebody who's a language expert, you could just start right with junk. So some of these examples that are in here were done to people who really had just a ton of language experience. But they had no circuit experience. This was the only time they built circuits. So, you know, there's a trade-off. All of you, by the time you get to that same level, will have had a ton of circuits courses. So you're going to have an advantage on that side. And you're just getting this course also a year earlier than they did. For them, it was a junior level course. For you, it's a starting sophomore. So that's why there's some differences on some of the problems. And I probably should rewrite the problems, but that's like, yeah, when I get free time. So it's not wrong, and it's not necessarily bad for you to look at it. Eventually, you will start doing stuff like that. Once you're comfortable, and I just want you to know exactly why you're doing it or not doing it. That you look at that and you go, oh, when it truncates, like here, I could stick other zeros and the truncation won't do it. But on the other side, if I stick a bunch of zeros, it'd be shoving that X over to the right. Because what matters is this side. This is the side that everything is referenced to. There's nothing magic about that. I mean, you could reference either side, but it does reference this side for how many bits do you take. So that's the one that you've got to make sure you hold. But I think it's even better if you get used to that. So I guess my suggestion is be really pedantic right now, right? Put all your ones and your bits and everything. Other questions?
I'm out of questions on the practice test, but I have another question about the homework, if I could have that.
There's, what, about 10 more minutes before I have to start setting things up for the next class, so.
So when we're doing an encoder to decoder, and I have to go from gray to binary, do we just convert? It just seems too simple.
It is that simple. That's the whole reason we love it, is because it is that simple. Right? You just write the patterns out. The easiest way I know to do it is to put the codes, write the binary codes inside the encoder-decoder pair.
Thank you, see you in class.
All right. Oh, you're welcome. All right, just write the patterns in binary. Maybe, yeah. All right, so I write out all of my code patterns here on the decode side. And I would have the same thing over here. All right, so on and so forth down. And you just match them. You just say, on binary, 0, 0, 0. In gray, it's 0, 0, 0. Right? And you just connect them across for whatever it is. This is 1 in decimal, and this is 1 in gray. This is 2 in decimal. This is 2 in gray.
Okay, so it's just a conversion.
Yeah, really, you're literally drawing the line between the codes that mean the same thing. And this is binary to gray, and if you mirror it, it becomes gray to binary. Because not all codes are right. You have to reflect them. It's not the same forward and backwards. But that's really all there is to it. That's why we like it, right? Anything that is really crazily simple that lets me accomplish something, it's worth noting. So any others? No? Awesome. I'll get some time to drink tea before class. You are very welcome. I should stop the recording and